Okay, let's get back to the class. So let's continue to talk about this minimum spanning tree problem. So where in general, we have a graph like this, and we want to consider like a connected subgraph, and basically want to make sure the summation of lengths of all the edges is as cheap as possible. So let's actually make this more formal in this graph sense. So for each pair, Vij have an edge between for a certain cost. So here, basically, we have a weighted. Here we talk about the undirected graph. So instead of like in the case of Dijkstra's algorithm here, we just in general, for instance, in this communication network problem, we just consider undirected graph, and basically, I mean, the same like from U to V and V to U, and actually, if there is an edge like this, we can consider both directions, and basically they have the same cost. So for our convenience, we consider weighted undirected graph G equals to VE, where each edge is associated with a positive cost. And we denote this as C of E, which is larger than 0. So without loss of generality, we assume different edges have different weights. So the goal here is then basically want to find a subset of edges, subset of E, so that VT is connected. The graph VT is connected. That is basically suggesting the edge set is a subset of the original edge set E here. But vertex set is the same. So we want to make sure the original vertex set, I mean, on the subgraph is still connected. And the cost summation belongs to TC is minimum. So here you see I'm using the capital letter T here, I mean, for the subset of edges. So that's probably suggesting, I mean, I'm talking about minimum spanning tree. I mean, this is probably suggesting a key observation here is that let T be a minimum cost net, be a solution, and VT is a tree. So I think intuitively you can imagine this because tree is a connected subgraph. I mean, it is connected graph, and also it does not have cycles. I mean, if there are a lot of edges, I mean, if it's far from the tree, it should be quite expensive. And actually, this is relatively easy to prove. I mean, by definition, VT is connected. So if T is not a tree, so due to our discussion, so basically connected plus connected, it suggests that it must have a cycle. So deleting an edge in the cycle. So we'll basically just decrease the cost. We'll keep the connectivity. And thus a contradiction. I mean, if it is not a tree. So any questions? Is this straightforward to you? Okay. So now we design an algorithm to find this. For this minimum spanning tree problem. So minimum spanning tree. So for our convenience, we use the acronym MST, basically the first letters for this problem. We consider this MST problem. So maybe let me also pause here for a few seconds or maybe a minute. You want to think about, I mean, I'm talking about greedy algorithm. How you want to use like a greedy strategy to solve the MST problem? I mean, where are like the points that we can actually make it to be greedy? So here I can think about, for instance, the following strategies. So here, maybe one specific kind of strategy, I mean, we are doing a greedily is that we can consider at cheapest edge. So what do I mean by that? Maybe let's, for instance, consider something like this. So let's successively inserting edges from in order increasing cost. So basically at the beginning, we can have a sorting. I mean, we have all the edges, I mean, and their corresponding cost. We just like sort them and we add edges from the cheapest to the most expensive, and basically in this kind of sense, and we successfully inserting edges. So as we go through edges in increasing cost order. So we do this. So we insert each edge as long as it does not create a cycle. And add it to the edges we have already inserted. I mean, you can imagine that, I mean, we keep adding from the cheapest to the most expensive. I mean, at a certain point, we are, of course, going to incur some cycles. But as long as we have cycles, I mean, if on the other hand, inserting E would result in a cycle, we just discard. We just discard E and continue, I mean, to the next edge in this increasing order of edges. So you can see that clearly this is a very greedy strategy that we figure out the way that basically the point that we are making this greedy is that we keep adding the cheapest possible edges. So at the beginning, we have like a sorting. I mean, we sort all the edges as this increasing order, and we keep adding the cheapest edge. I mean, at some point, maybe there are some cycles, and having a cycle this well as the definition of the tree. So we just discard it and continue to the next possible edges. I mean, the next cheapest edges, and we keep adding until it finishes. So basically, this approach is called the Kruskal's algorithm. Kruskal's algorithm. So any question about the definition of Kruskal's algorithm? Okay, so this is basically one strategy that we can think about. I mean, to solve the MST problem, we just keep adding the cheapest possible edge. But maybe we can also consider, on the other hand, another like similar strategy, but also sounds a little bit different. We can consider something like this. So we increment the spanning tree in a cheapest way. So what do we mean by that? We consider such kind of procedure. So we maintain a set S, which is a subset of V, on which spanning tree has been constructed so far. So initially, I mean, we just like maybe we start with some certain random vertex. We start with say S equals to S. So in each iteration, we grow S by one node. So it depends on which node we want to add. So we add the node V, minimizes. Basically, we want to talk about the MST. We want to make sure that adding a new vertex is, in some sense, does not increase the cost a lot. So this is something we want to keep in mind, and we call this like attachment cost. So what do I mean by that? It's basically the mean of all the E, UV, and here U is in the S, and E is basically in the H set. Want to consider like a mean of adding such that this cost is the minimum, and basically we add edge E. Choose this minimum in the spanning tree. So this strategy or this approach is called the Prim's algorithm. Called the Prim. So here we see that basically, let's take a look at both the Kruskal's algorithm, also the Prim's algorithm. So we see that the strategy is actually, you can see from the spirit level that both algorithms, they are actually greedy, but they're doing greedy in different things. So Kruskal's algorithm each time keep adding the cheapest possible edge. I mean, when you run the Kruskal's algorithm, you are not necessarily, I mean, at the very beginning, you have like a spanning tree. But actually, Kruskal's algorithm, they're pretty sure that each time they're adding the cheapest possible edge, as long as it does not incur a cycle. But on the other hand, you can see the strategy of the Prim's algorithm is that you want to keep to make sure that the current subgraph you're having is a spanning tree. Although I mean at the beginning it is a small tree, does not contain all the vertices. But as long as you run the Prim's algorithm, it is always a spanning tree. And after the algorithm finishes, it is going to be a spanning tree of the whole set. I mean, it is important that here we grow S. We grow S here by a node, adding a node V here. So basically in this definition, this V here is not in S, and basically U is in S. So basically we want to add like the cheapest edge that is between S and V over S. And each time basically, because we add a new vertex into this graph, this is keep going to be a spanning tree because you are making a new vertex connected to this, and this should not incur any cycles. So basically, you can see that by the definition of this Prim's algorithm, the graph that you are finding, it is always kept to be a spanning tree, and we want to make sure that finally, hopefully, I mean, after the algorithm finishes, this spanning tree is good. That basically, hopefully, there's a minimum spanning tree. So, is there any question about like the definition of Kruskal's algorithm, Prim's algorithm? Okay, so now we are going to give some analysis of both the algorithm and to see actually whether they are correct or not. So here I think to basically give a good understanding about both algorithm, I think we need to have some tools that basically want to understand what properties a minimum spanning tree, an MST, should contain. So basically, we consider such kind of lemma. Or I think here, when is it safe to include an edge in MST? Crucial. So here, it is a lemma like this. So let S be any subset of nodes. That is, we don't want to consider uninteresting cases. So we assume that S is neither empty nor equal to V. I mean the whole set. And let edge E goes to VW should be the let I think it should just be the minimum cost edge with one end in S and the other end in V over S. Then every MST contains the edge. So we see that this is a lemma that we want to prove, and we see that this is really a strong lemma that in general, I mean, we consider an arbitrary S here that is neither empty nor equals to V. We consider any such kind of S, and basically we consider the relationship between S and V over S. And we consider correspondingly the minimum cost edge between this S and V over S. Then every MST contains the edge E. So this is really something quite strong that we want to make sure that every edge, I mean, every MST can contain such kind of edge E. And actually, this is something quite interesting. So we prove this by a contradiction. So because we are talking about, I mean, every MST should contain the edge E here. I mean, if we consider the contrary, then it should be the case that assume a T is a spanning tree. Oh, I think I should probably say T is a minimum spanning tree. Maybe let me do this. Minimum spanning tree that does not contain E. So basically, we need to show that T, I mean, we need to find a contradiction that basically we need to show that T does not have the minimum possible cost. And then we get a contradiction. So the intuition here is that, I mean, we want to show that it does not have a minimum possible cost. Maybe a good strategy is that we want to make some switch. I mean, we point out there's another spanning tree having like the value, I mean, corresponding cost even smaller than the current tree T here, then basically we are actually good here. Or I think maybe we can say the intuition is that we will define an edge E prime in T. It is actually more expensive than E. And basically, we actually just want to utilize the property of this E being the cheapest edge between E and between S and V over S. And if we can figure out like another edge E prime that in T that is more expensive, and hopefully, I mean, after exchanging E for E prime can result in another spanning tree. Then this gives the contradiction we want. Okay, so I think basically we need to figure out such kind of edge E prime that basically make the thing basically in this T, if it does not contain E, and actually this should be more expensive and cannot be an MST. So basically we need to figure out this. So let's to take a look at this edge. Basically want to take a look at this edge E closely. So recall that here we denote E equals to VW. And basically we know V belongs to S and W belongs to V over S. So T is a spanning tree. So there must be a path. Let's say the path is P in T from V to U. Oh, sorry, from V to W. I'm using W here. So what do I mean by that? So let's just consider something like this. So basically we because we are talking about this edge E to be the cheapest edge between S and V over S. So let's just draw the S here. So what is happening in this tree T here? So we have this V here and we have this W here. So we know that there's no, I mean, this edge, I mean, between V and W, this is not in this tree T here. But nevertheless, we know that the T here is a spanning tree. I mean, this is a spanning tree. So there should be a path. I mean, for instance, maybe can be something like this. I mean, it can be something like this. And hopefully, for instance, like this is connected, this is connected. Because it is a spanning tree, so there should be, after all, there like a path, I mean, P from V to W, I mean, at somewhere. So we actually take a closer look at this part. I mean, what do I mean by that? So we consider this. So there is a first node. W prime on P. It is in minus. I mean, we consider the first time that, I mean, the P is a path from V to W. So at the beginning, this P should be inside the set S here. So we consider the first time that actually it goes out of this set S here, and let's call this a W prime. Oh, this is not, it is W prime. So let's consider the first time that this is an edge. And we can also similarly define a V prime to be the node just before W prime in P. So by just before, I mean, it is basically this node. And due to the definition that the W prime is not in V over S, and it is the first such kind of node in this path P here, the V prime should belongs to S. And actually, we have such kind of path here. So we consider this strategy. So we exchange for E prime, where E prime is basically this edge, this V prime W. So basically, I mean, this P is a part of the T here, and we consider strategy now. We don't have this edge, and we instead have an edge between V and W. So basically, this is what we mean here. So let's see what is going to happen. So this gives a new tree. E prime, which equals to T, we minus the edge E prime, and we actually have the edge E here. So let's see the property of this tree T prime here. So we notice that actually V T prime, it is connected. So this because the switch does not influence the connectivity. So in particular, I mean, we talk about connectivity. I mean, it's basically about like two vertices and whether they are like paths between these two vertices. In particular, for two vertices, both in S or both in V over S, this is just trivial because the switch does not influence this. For two vertices, I mean, one in S and the other in V over S, we consider something like this. It is connected by going to V, V to W, and W to the desired. So because basically inside S and inside V over S, it is connected. So basically after switching, we can still search for this kind of connectivity by going through the edge of V to W. And I think on the other hand, we know that Vt prime, it is actually a cyclic. This is because the only cycle, I mean, if we consider both the edges E and E prime, so the only cycle in V and actually T prime with the edge E prime, the only cycle, I mean, if we have both these two edges, the only cycle is going to be P. I mean, this path with V and W. This is the only path that we can actually have this edge incurred, but actually this is removed. Due to deletion of E prime. So furthermore, I mean, this really goes to the greedy part that basically we want to use the definition of the edge E here. So we note that edge E prime has one end in S and the other in V over S. But actually, due to the greedy thing that E is actually the cheapest edge with this property. So that is going to say that the cost of E is smaller than the cost of E prime. So therefore, the cost of T prime is smaller than that of the cost of the tree T here, which is actually as the desired. The contradiction is reached. And this finishes the proof. So any questions? So basically for using such kind of argument, you can see that this is typically the intuition of how greedy works. I mean, you think about like you want to design a greedy algorithm for a specific problem. It must be the case. I mean, maybe like the minimum of some kind of thing is like the solution must actually have this kind of the minimal I mean according to some kind of rule. I mean specifically this basically this lemma shows a very important thing that for arbitrary S here, I mean for S and V over S, because we talk about minimum spanning tree, it always has the connectivity. And basically you see that in this proof, we actually utilize this kind of connectivity that basically for the part S and for the part V over S, and we consider all the edges between S and V over S, and basically for the edge with the smallest cost, it should be contained here. Okay, so if there is no question, I think, of course, the next important thing is that we are going to prove the results. I mean, theorem. And basically, we want to show that Kruskal's algorithm, Prim's algorithm, they are actually correct. So basically, Kruskal's algorithm produces an MST of G. to prove. So by the very beginning definition of Kruskal's algorithm, I mean, Kruskal's algorithm does not necessarily maintain a spanning tree. So we really need to be careful. I mean, maybe the output of Kruskal's algorithm is not connected. I mean, this can also be possible, I mean, in general. So we want to have a very careful argument about, like, on the one hand, it outputs a tree, and also on the other hand, it is like a minimum spanning tree with the minimum cost. So let's do the argument like gradually. So let's consider any edge EUV added by the Kruskal's algorithm. And let S be the set of all nodes to which excuse me, to which we has a path at the moment. Just before E is added. So what is the point of considering this S? I think basically when we want to use this lemma, we want to when we want to use lemma, we need to figure out what is the set S here. Basically, we have this S and we have this V over S, and we want to utilize the property that this E, I mean the edge with the minimum cost between S and V over S is always contained in this MST. We basically want to utilize this property, and so basically in this Kruskal's algorithm in analysis, how do we want to do this? The way that we want to do this is here, that basically we want to find like a connected component. I mean, basically as defined here, we basically can consider a set of all nodes to which we has a path at the moment. So this is basically going to be the S that we are going to apply. And actually by the definition of S, so no edge between S and V over S has been added. I mean, this is just due to the way we define S here. I mean, the set of all nodes to which we have a path at the moment. I mean, if there is an edge, I mean, otherwise S could be bigger. So this further implies that all edges between S and V over S have large weight. Have weight actually larger than CE. Otherwise, such an edge should have been added by the Kruskal's algorithm. And basically, we are talking about two sets, I mean, S and V over S. They currently don't have any edges. I mean, in this case, at one edge does not create a cycle. If basically both ends of the edge you added, actually they are even not they're actually even not connected in original graph. I think such kind of edge does not create any cycle. So should not, I mean, back to our argument here, should have been added by the Kruskal's algorithm, and actually does not create a cycle. So basically this basically confirms that all the edges between S and V over S has this weight at least a CE. Sorry. Yes. So this is basically great, and this is actually promised by the Kruskal's algorithm. And actually, we say that therefore, E is the cheapest edge I mean, let's say that this. So with one end in S and the other in V over S. And this, I mean, by our lemma, E belongs to every MST. So this is pretty good. I mean, this suggests that Kruskal's algorithm is correct in the sense that everything it adds is actually belongs to MST. It basically remains to prove that the output Vt of Kruskal's algorithm. We just want to make sure that it is a spanning tree. I mean, if this is not a spanning tree, I mean, this does not make sense. But because every edge, I mean, every edge of the Kruskal's algorithm outputted by the Kruskal's algorithm belongs to the minimum spanning tree. I mean, if the output of a Kruskal's algorithm is a spanning tree per se, we know that the solution is optimal. I mean, we can still by a contradiction argument. I mean, if the output is not a minimum spanning tree, then there should be an edge. At least it does not belong to one of the MST. Sorry, at least there should be an edge that does not belong to every MST. But this just contradicts with what we have been talking about. So the only remaining thing that we need to make sure is that the Kruskal's algorithm it always output a spanning tree. So let's do this. So clearly, Vt, the output of Kruskal's algorithm has no cycles by the definition. It's just in the definition of a Kruskal's algorithm. I mean, each time it would result in a cycle, we just discard the corresponding edge. So I mean, basically by the definition of Kruskal's algorithm, we should never have any cycles. So the only remaining thing that we need to confirm is that the T is connected. So let's also argue this by contradiction. If not, there exists a non-empty set as of nodes such that there's no edge between S and V over S. I mean, basically, you're assuming that the output T here is not connected. Then basically, you can, of course, having such kind of division of S and V over S that there is no edge between them. But this actually contradicts with Kruskal's algorithm. So because there is actually at least one edge. Oh, I think I should probably mention at the very beginning that here, the graph that we are talking about is a connected graph. I mean, other than that, I mean, it does not make any sense to talk about a minimum spanning tree problem because it does not exist. So we always assume that the graph is connected. I mean, in this sense, there is at least one edge between S and V over S. And Kruskal's algorithm I mean, consider how you would like to run the Kruskal's algorithm. I mean, at the time, I mean, you actually encounter, I mean, you have this kind of increasing order of all edges. I mean, Kruskal's algorithm is going through all of these edges. When it encounters that edge, I mean, there is no edge between S and V over S. And Kruskal's algorithm will actually add first of this. It encounters. But you say that S and V over S, they are disconnected. I mean, this is just contradiction. So this basically finishes the whole argument. So this gives the proof of the Kruskal's algorithm based on our key lemma. I mean, basically this lemma that for any s, I mean, between s and v over s, I mean the edge with the cheapest cost, it should belongs to every minimum spanning tree. And basically we make this argument, and basically we first show that all the edges output by the Kruskal's algorithm, they should also belongs to every MST. And also the output of the Kruskal's algorithm, it also gives us spanning tree. So that basically makes sure that the output of the Kruskal's algorithm is correct and actually gives a minimum spanning tree. So is this argument clear to you? Sure. Oh, that's a good question. So here by the assumption, so here in this discussion, we assume actually we assume different edges have different widths. Yes, this is assumed in this argument. And actually, let's make a remark here. And actually, this is a very good question. So remark. So what if we have edges with the same cost? So there are different strategies. So one strategy is to perturb all edges. I mean, I should say all edge costs by different. I mean, different, but extremely small numbers, so that they become distinct. So that basically address your question that what if they have equal weight? We just like shifted like in a very tiny sense, and then we run a Kruskal's algorithm or Prim's algorithm. So as long as true costs that are differed originally still have the same relative order, we are good. So basically one strategy you can imagine is just like we shake everything by a little bit. And because we are talking about like the minimum spanning tree, and this minimum is taking, I mean, among others, I mean, we want to make comparisons. As long as if you shake it tiny enough such that, I mean, relative order of all the costs does not make a difference, basically we are good. So for instance, maybe let's do something like this. So for instance, let's consider a case where the cost of all the edges, they are natural numbers, I mean, positive integers. So in this case, we perturb all edges with a noise C plus, or basically this cause C, we assume that this noise is non-zero, is smaller than 1 over 2n for so this is good because, I mean, if we want to talk about, for instance, like the cost of different spanning trees, I mean, if they differ, I mean, all the edge costs, they are natural numbers. I mean, if the cost of different spanning trees they differ, they should be differed by at least 1. I mean, but each spanning tree, I mean, they have at most they have exactly n-1 edges. So if the noise of each, I mean, is at most 1 over 2n, then basically you are good. I mean, and also different noise. But I think this is still like a caveat, because what if, for instance, I mean, we don't assume that all the edges have natural numbers, and basically the perturbation of this noise should be, you should be much more cautious on this. I mean, for the use and basically for the I mean the presentation of the algorithm, we just with all of generality, we assume that the cost of different edges, they're different. But if they are the same, maybe for some specific scenario, you can actually deal with. But in general, we need to be a little bit cautious for You want to be a little bit more careful here. So because you want to specifically, we want to be careful about the lemma here. I mean, the lemma here, because minimum spanning tree, I mean, if the value are same, it is still the minimum. It will break the lemma actually. You see, for instance, if for instance the edge, I mean, if the E prime and E they have the same, if they have the same weight exactly, I mean, this lemma is actually not working. So this is actually a tricky part, and actually why in this specific scenario, I mean, for instance, in some of the algorithm, for instance, in the first class, we talk about the slope matching problem. It is fine that, I mean, if there's like a tie break, you just like choose arbitrarily. But here, I mean, in the specific argument about this lemma, I mean, if the weight of the E prime and E, they are the same, you cannot easily say that every MST is going to contain the edge E here. So this is a tricky part, then why I'm saying that we probably need to add like a perturbation to solve this issue. Okay, so I think we basically proved the Kruskal's algorithm. So Prim's algorithm. So the proof is also actually a straightforward, relatively straightforward. So I think we only have like 3 or 4 minutes. So I think I won't like show the details here. But I think I will upload this in the online version. So basically, I think you probably noticed that after each lecture, basically tonight, we will the TA will upload the lecture note and basically the video and also some announcements if there are. So basically, we will update the proof of the Prim's algorithm in the lecture note tonight. So I think the last note that we want to make is that the implementation cost. The implementation cost is actually O of, similar to the Dijkstra's algorithm, the implementation cost is O of M log n of the Prim's algorithm. So basically, each time we maintain a spanning tree and adding an edge that keep this to be a spanning tree, but it's the cheapest among all such kind of possible edges. So here, recall that we actually only write O of M log n here, because by the definition of the MST problem, we assume the graph to be connected, which suggests that M is at least n minus 1. And so it does not matter whether we write M plus n or M here. So for our convenience, we just write O of M O of M times log n here, because we have the assumption M is larger than n minus 1 to make the graph to be connected. So this is actually also relatively straightforward. It's just that in the algorithm, basically we need to be able to decide which node V to add next to the growing set S. And basically we need to according to the definition of the Prim's algorithm, basically we need to maintain this attachment cost. And basically this is where it really looks like the Dijkstra's algorithm, and we can actually utilize this. And actually by maintaining the attachment costs, AV equals to mean of E W belongs to UV. So to S, E belongs to E, CE for each V plus 2V over S. So basically, we still use a heap, basically with AV as keys. And basically there are a -1 iterations, because each time we add an edge, the spanning tree is getting larger, and basically the spanning tree has at most n-1 edges. So basically there are at most n-1 iterations in which we perform extract mean, and we perform a change key. Similar to the discussion of Dijkstra's algorithm, also at most once for each edge. Okay, so basically this finishes also the introduction to the minimum spanning tree problem. And I think due to basically this class has over, so I think maybe I should probably stop here. And I think basically as a summary for today's class, we start to introduce the greedies algorithm. And I think because for the last class, we have been talking about graphs. So basically this class, we talk about two very important problems using greedy on graphs using greedy algorithm, basically the Dijkstra's algorithm for the shortest path problem, and also for the minimum spanning tree problem, we introduced the Kruskal's algorithm and the Prim's algorithm. Okay, thank you for your attention. See you next week.